Hello and welcome to this video. So we're trying to solve this expression over here. We're trying to find the inverse Laplace transform of y of s. But we have s to the power 4 in the denominator. Now we have already solved this. We solved this in the last video and we arrived at a solution that we have on the right hand side here as the inverse Laplace transform to if we hadn't had that s squared in the denominator. Now let me actually factor out the s squared out of the denominator so that we end up with something like this being equal to s squared into s squared plus 2s plus 7. Now, if all we had was 3 over s squared plus 2s plus 7, we have a solution already. But we have this s squared here, and we haven't quite decided how to deal with it. Now, it makes sense that this expression we have over here can probably be written in this form. Say, let's just say a constant, let's call it k1, divided by s squared plus, I'll leave a little gap over there and then just write 3 over s squared plus 2s plus 7. Now, if we could find a way to write this expression as k1 over s squared plus this, then we have a solution. Because for this parameter, this 3 over s squared plus 2s plus 7, where for this expression we already have a solution. And for this first expression here, k1 over s squared, we know the solution to that. The inverse Laplace transform of that is simply k1 multiplied by a ramp, by unit ramp. So we can solve this. But one question we first need to address is this expression that we wrote here equivalent to this? Well, to a large extent, the answer is yes. But then, what if we had had a k2 over s? What if I had that? Will that still be equivalent to this? The answer is yes. Okay, so the question is, how should we deal with this kind of a system? So, if we can get this into this form, that is called partial fraction expansion. Okay, so partial fractions expansion. So we're trying to expand a particular fraction into partial fractions. Okay, so we're trying to expand this into partial fractions. So we now want to talk about partial fractions. And for partial fractions, there are a number of things you want to think about. Now, in reality, before we arrived at this solution over here, we should have asked ourselves some questions. Okay, so there are a number of possibilities you could have with partial fraction expansion. When you have a fraction that you want to expand, it is possible. So I'm trying to tell where to just write them out. Okay, so let's say there are a couple of possibilities you could have. One, you could have real and distinct roots. How we expand a particular fraction is dependent on the roots of the denominator, okay? Dependent on the roots of the denominator. So you could have real and distinct roots, or you could have real but repeated roots. In other words, some roots that exist more than once. Excuse me. Or you could have complex or imaginary roots. Okay, I hope you can read this. So you can have real and distinct roots, or real repeated roots, or you could have complex or imaginary roots. Okay, so to make sure that everyone can read what is over here, maybe what I should do is actually write them properly so that they are very legible. So let's just reduce the font size of that. Will this suffice? No, let's take it down to 20 something. Let's say 26. Okay, so hopefully this will be fine. So we could have, just give me one moment. So we could have, I do apologize. So we could have real and distinct roots, or we could have real repeated roots, or we could have complex or imaginary roots. Okay, so these are the three possibilities that we could have. Can I move this on top of that? It will not overwrite. Okay, so I need to get rid of that first of all. I do apologize. I just get rid of this. I'm sorry. Let's get rid of this. And then let's just move this to one side if it does not complain. Okay, so those are possibilities that we could have. We'll deal with them one at a time. Okay, so let's deal with this one at a time. So it's possible that we have real and distinct roots. So in case one, that's real and distinct roots now. That's our first case. So let's take an example on that. Let's say we have a system. We're told to find the Laplace transform of, say, 2 over s squared plus 3s plus 2. We're told to find the inverse Laplace transform, I should say, of this. Now, if you want to find the inverse Laplace transform of this, a quick look at this, well, maybe not a quick look, but you can probably tell by looking at the denominator that what you have can be, that this can be easily decomposed into s plus 2 and s plus 1. Okay, so we can decompose the denominator into s plus 2 and s plus 1. In case it's not very obvious that you have real and distinct, so this, you have two roots here in your denominator, -2 and -1. They are real and they are distinct. None of them is complex. Now, one of the quick checks you could always do, if you remember the quadratic formula or the quadratic equation, let me put that up and not put it down here. So you have your x is equal to, if you remember this, minus b plus or minus the square root of b squared minus 4ac. And all of this divided by 2a. Okay, and this is for the general system where you had ax squared plus bx plus c being equal to 0. Okay, so if we had that, then your quadratic equation is negative b plus or minus square root of b squared minus 4ac over 2a. The reason why I bring this up is what determines whether the roots will be complex or not, particularly complex or not. In fact, what determines whether they will be complex, or in fact, which of these three cases, whether it is real and distinct, real and repeated, or complex or imaginary, what determines that? What determines that is what you have underneath this square root sign, b squared minus 4ac. Now, if your b squared minus 4ac is less than 0, if it is less than 0, then what you will have here will be a complex, your roots will be complex. It will be minus b plus or minus something I divided by 2a. No matter what b is, no matter what a is, assuming they are both real, your root will always be complex. There will be complex conjugates, something plus something I and something minus something I. You will definitely have that if your b squared minus 4ac is less than 0. In other words, if your b squared is less than 4ac, then what you have are complex or imaginary roots. Let me go ahead and write that here as b squared is less than 4ac. Okay, so that is your case 3. Your b squared is less than 4ac. That means that you have complex roots. Let's take another case. How can we know that our roots will be real? Now, well, if your b squared is greater than 4ac, if your b squared is greater than 4ac, then what you will have here, this square root here will be a positive real number. Your b squared minus 4ac will be a positive real number, and you have minus b plus a positive real number minus b minus a positive real number, all divided by a. In other words, you will have real and distinct roots if your b squared is greater than 4ac. And the third case, I think this probably goes without saying, if b squared is equal to 4ac, then you have your real and repeated roots. Okay, because this expression here will be 0. That will mean that your x will be equal to minus b over 2a twice. In other words, minus b over 2a plus 0 minus b over 2a minus 0. Okay, so we have a a system we can work with. And whenever you have a, a quadratic equation or a quadratic expression in your denominator, then you want to simply run that test. So let's run that quick test here and see. Our b in this case is 3, so b squared is equal to 9, and our 4ac is equal to 4 times 1 times 2, which is 8. 9 is greater than 8, therefore we expect to have real and distinct roots. We know we're in a case 1 situation. So we are in a case 1 situation, even if it is not very obvious by looking at this expression. Okay, but having said that, we know we're in a case 1 situation. So what we have is this over here. Now, if we have a case 1 situation, then what we have now, this our expression is, so what we are now trying to find the inverse Laplace transform of 2 over s plus 2, s plus 1. Now, this expression can be written as k1 over s plus 2 plus k2, that's any constant, over s plus 1. So any constant over s plus 2, any constant over s plus 1. This is our new solution. This is our new expression rather, and we know that this solution is simply k1 e to the power of minus 2t plus k2 e to the power of minus t. Okay, because 1 over s plus 1 is the inverse Laplace transform of 1 over s plus 1 is e to the power minus t. Inverse Laplace transform of 1 over s plus 2 is e to the power of minus 2t. K1 and K2 are simply constants, so they come on the outside. So we have a solution to this, but we don't know our K1 and we don't know our K2. How can we get K1 and K2? Well, there are a number of ways. There are two ways primarily that people do this. One is kind of easy. Let me start with that. And then we have K1 over s plus 2, sorry, plus k2 over s plus 1. Let's work backwards. This is the same thing as saying k1 into s plus 1 plus k2 into s plus 2, all divided by s plus 1, s plus 2, or s plus 2, s plus 1, same thing. Okay, so if we just simply combine this together into a single fraction, your denominators multiply out, you have s plus 2, s plus 1, and then you now have k multiplied by s plus 1 and k2 multiplied by s plus 2. Now, comparing this with what you had originally, this is simply equal to what we had originally, which is 2 over s plus 2 or s plus 1, s plus 1. Okay, so we have this being equal to that. This simply means that our numerators are equal. Okay, denominators are equal, so the numerators are equal, and our numerators are, the numerator on this left hand side is k1s plus k1 plus k2s plus 2k2. Okay, okay, so let's, since I have an equality sign here, so I just include the denominator, s plus 2, s plus 1. Now we want to equate the numerators. So we're simply saying that 2 is equal to k plus 1, k1 plus k2 into s plus k1 plus 2k2. Let me just check I did that well. K1 plus k2s and k1 plus 2k2. Yeah, good. So this expression is equal to that. Take coefficients and equate your coefficients. So if we want to equate our coefficients, we have that our k1 plus k2 is equal to 0 because there's no coefficient of s on the left hand side. And from this expression, we know that our k1 is simply equal to minus k2. And the second coefficients we equate tell us that our k1 plus 2k2 is equal to 2. Now we already know that k1 is equal to negative k2, so we can put negative k2 in here. This is equal to minus k2 plus 2k2, which is simply equal to k2. So we discover that our k2 is equal to 2. So k2 is equal to 2, that means k1 is equal to negative k2. So let's just now write our solution here. We have k1 is equal to minus 2, and our k2 is equal to 2. Okay, just put that in a box so that it's easy for us to recognize. And now with this solution that we have, we can now arrive at our solution here as being equal to minus 2 e to the power of minus 2t plus 2 e to the power of minus t. The Laplace transform of this will be equal to 2 over s squared plus 3s plus 2. Okay, so we have found the inverse Laplace transform of that to this. What we did was we decomposed this into partial fractions, k1 over s plus 2, k2 over s plus 1. Those are the partial fractions. We decomposed it into that, and we were now able to come up with a solution. Okay, so this video is already 15 minutes long, so I'll stop at this point and continue in the next video.